all of your fantastic faculty you have here at NC State. Jack and I, we shared an office at NASA many years ago, and I always wanted to, when I grow up, to be just like him. And before him, we had Professor Hassan here, and he was one of the premier in my field, and yeah, Tarek is going to come back, one of the major guys in the field of combustion. So, really good school. So it's really nice to be visiting you on campus. And as beautiful, let's see.
And you just click on the mouse.
Oh, with the mouse, okay.
How do you? No, I'm checking. I think it's kind of
okay. Yeah. As beautiful as your city is, Pittsburgh is also very, gorgeous. We do get a lot of snow, and we are very nice both at night and day. So if you're ever in that area, it's just one of the nicest areas, and close to the downtown of Pittsburgh. That's where the University of Pittsburgh is, and that building that you see there. I don't know if I can use any of them.
I think none of them are working.
No, okay. Well, just
yeah, you can use the mouse.
Okay. Yeah, so this building here, Cathedral of Learning, is the second tallest academic building in the world. The first one, the tallest one, is in Moscow, and the one in Moscow, half of the building you can't go. So the top floor dangerous. So we say that we have the tallest academic building. Oops. Let's see if I can go back. This is
right click and then go. Previous.
Previous. Second. Yeah, just one. I have to. This is my. But I promise for the rest of it would not be as bad. Okay. One more. Okay, so what I put this name here because it seems that your chair knows all of my former students and colleagues. So I had pleasure of working with a large number of very, very good students, and only listed only the PhDs. I don't know if here you guys list your master's students too. We really don't. We only list the PhDs, and a lot of them ended up going to academia. And some of them are doing really well, but the reason I put this thing in here is because the academic national lab and industry is that where mostly aerospace and mechanical engineering students go. But in my case, though, it just happened my last PhDs and latest one, they just happened to go to data firms. They just getting 3 times as much of a salary as a professor and a research scientist. So. A lot of the last one of my set of my students are going to the software companies and to the data firm. The kind of things we do, which is just seem to be more interested in doing computations, and if you're in the data sciences and all that, it just happens to be going there. So, anyways, it's been a pleasure to be working with them, and I will be showing some of the work of these people. So. You guys here at NC State, I don't have to talk so much about it, but the importance of combustion and turbulence has been there since the mankind has been there, and major part of aerodynamic and propulsions. And you have the world experts here in all of this field. So as you know, that's an area. If you're working in the field of aerodynamic and propulsion, the aerodynamic and engine propulsion is one of the most important part of the aircraft. That's the most important part of the aircraft to be concentrating on. And it goes for both external flows. Any of those your calculation? Because I stole them from NASA. So And internal flows, that's where the combustion is of primary importance, and also for, for the future, and all the other things that is outside of what we do on everyday thing. If you want to do supernova, that it just seems that DOE is very much interested in it. Combustion is a very important part of it, and a major part of the energy consumption that, is even in the foreseeable future, combustion seems to be a major part of the energy usage. Now, this part you already know. But now what has been happening within the past, 5 to 10 years, there has been this two major revolutions affecting combustion field. One of them is the big data revolution, and the other one is the second quantum revolution. Both of these revolutions have been major impact in other fields, and are starting to have some effect in the field of combustion as well. And for those of you, as you already know, in paradigm of science has been always on theory and experimentations. Back in the 80s, that people came up with the field of simulations. Simulation that called them as the third pillar of science. That in addition to theory and experimentation, you can simulate, things that, with the use of computers. And now the fourth paradigm that is with the emergence of data. If you have a model and you have a data, that's what the data sciences are becoming very important. So these are now, as we know, combustion scientists and turbulence people have been moving along with this thing. They've been going through the simulations, and in fact, one of the major advancements has been done in field of simulation by turbulence people, computational turbulence people who made major impact in the field of simulation. And now with the data is having similar effects. And also this thing with the computing platforms, as you know, starting in with a card punch back in the 50s and 60s, and going on and going to the parallel to the massively parallel computations. But if you look at the way this computing have been going on for the past many years, the field of the Moore's law that's saying that the computers are supposed to be upgraded every 18 months or so, doubling the speed every 18 months. There seems to be a plateau in that curve. The one on the right is the one that, the green one is the original Moore's law. Even though Moore's himself never said it. They refer to him as the Moore's law. But the orange is the one that is basically happening. So, and every year there is a competition, which school has a better, or which country has a, bigger or better computers and all that. So what is happening as these chips are getting smaller and smaller, is come to a point that the speed up in the computation cannot keep up with this. And I have been doing turbulence computation for the past 40 years. So I have seen this incremental of changing the computer, and we are doing faster and faster computation. But we are getting to that level that increasing the Reynolds number with the supercomputer is not becoming that much anymore. So what is the solution? What can we do? What would be a way of going around this problem? And quantum computers, some people think that might be a way of dealing with this situation. So we have quantum computing and we have big data. And what we like to do to say that, okay, how can we use ideas from machine learning, artificial intelligence, deep learning, and also from quantum computing, in what way we can implement them in turbulence and combustion. Those are the fields that I know. So these are the fields that we want to use in order to deal with this problem. So we have been doing a lot of mixing and combustion experiments. And I think the group I was in at Flow Research Company in the 80s, we were one of the very first who did DNS of reacting flows. I think that was the first group that they did it. So since then, we have been continuously doing it, doing chemically reactive flows with realistic kinetics, with high Reynolds number turbulent on the right. So this right on the right is the kind of simulation that we are doing. And I did is my last PhD student who had done this really expensive calculations. And there is a whole bunch of experiments on the binary mixing and reactions that are out. And we want to know how we can use, in what way we can use deep learning and machine learning techniques, and also quantum computations for this. And so I'm going to go, this is the examples I'm going to go through. So I mean, there is a lot of math and computations in between. I'm going to eliminate them, but there's papers that, some of these papers, some of them are review articles that, you can, if you are interested, you can read to know all of the details. I just go through some of the stuff you have done. Okay, so, this problem, binary mixing and reaction, has a lot of applications, as you already know, and many of you are doing this calculation. So there are two things that we do. If you're a graduate student in this department, you know what they are. We approach the problem of turbulence and combustion in two ways. One of them is the brute force direct numerical simulations. We simulate the heck out of everything of it. So we are limited by the Reynolds number and Damcolor number and all that. On the other hand, we also do a lot of modeling of these flow problems, something that is known as the Reynolds average neighbor stocks and large eddy simulations. And we use stochastic models. We have the very sophisticated stochastic model for modeling of those. You guys have had, Dr. Hassan was one of the premier people in the field of RAND modeling. He does Reynolds average RAND modeling, Reynolds average neighbor stocks. We do it something called the probabilistic density function approach. And it's something I have been doing it for the past 30 plus years. And we have developed it for the context of the LES. So we have a basic set of equations for chemically reacting systems. The question, whatever way you want to write them, and what we would do, these equations, we either filter them or you average them. By filtering, meaning that you want to look at the smoother field, so it is not as expensive. If with LES, you pass it through a filter, and they look at the filter, make it smoother, and that filter by that filter function G is that what it is. And this filter has to have some properties, some mathematical properties, so you can do things correctly. So if you write the equations for the filter quantities that are given by these brackets, either by subscript L or capital L, whether one of them density weighted or not, and you can transfer the equation for them. And if you write for this equation for this thing, so this average quantities, like anything else, you would find a whole bunch of time that you need to model. If I take an course in turbulence, there's a whole bunch of these correlations that you need to know for energy equation, for momentum equation, for the scalar, and S, the capital source stuff for the chemical reaction. Those are the tabs that you need to model in order to close the set of equations. And this is that you already all know. And okay. This thing is okay. And for those second order moments that are within either the subgrid or Reynolds average, if you transfer the equation for them, those transfer the equation, they have either higher order term than you still need to model. This is a problem turbulence models have been dealing with centuries. Since the time of Osborne Reynolds, people have been dealing with this problem. Let's see. Okay, so the approach that we had adopted And now we see the relationship with everything else we are doing with machine learning and quantum computing. We look at this whole thing, there is something called either filter density function, if it is used in the context of LES, or probability density function that it is known in the context of Reynolds average neighborhood study. We look at all of the PDF, all of the statistical behavior of all the variables. So for example, if you have chemically reacting flow at low and high speeds, your transport variables are all the velocities, pressure and the energy, and these are decoupled, and all of the species. So in here you have the velocity v, the phi at the side, that is the scalars, and the pressure and the density, pressure and the energy, and the p is the PDF of them within the subgrid. And you can write the transport equation for that PDF. You can come up write an exact transport equation for it. And that equation is exactly written like that. But the problem with this equation is that, the beauty of it is the term on the left, the green term, that is the convective term, that appears in a closed form. So it means that all the Reynolds stresses and everything that other people have to model, you don't have to model. So that's the beauty of it. And if you have chemical reaction, it's an S term, that term is also in a closed form. So those are the good things. The bad thing is all the other terms that you see in that one, that is the conditional averages, you need to model. You need to model those terms. And for a long time, modeling of this term has been the problem with one of the major problems people having used them. In fact, at one point, I was at some of this program. People said that, what is this equation? To develop this equation, nobody understands. It is not that you understand it. It's just, they're giving the physics of the problem. So the way that we model them, it has been successful. We borrow from the field of stochastic. Stochastic, you write the stochastic differential equations to capture the physics to the best of that you can do. This is model, So model is never exact, so it is a model. So what we do, we look at all the statistical quantities, like velocities, concentrations, energy, and pressure, and we write a stochastic equation. Those are model vectors. And so that equation dz, the dt term is like a ODE, and then the W is the Wiener-Levy process, so it makes it a stochastic differential equation. And associated with that stochastic differential equation, we have a Fokker plan that basically tells you what your model PDF is. So that's the way we model this. And how we model them, there is a whole art and is an art into it. Now, this kind of calculations, the way these calculations are being done typically now, typically you need order of, if you want to do LES, the way the state of the art is, LES with this, you need something in the order of 1 billion or several billion grid points with an order of magnitude more Monte Carlo particle to do the simulations. This calculation was done when this method was developed, was transported to ANSYS, and these are the calculations done by the ANSYS computer code that are doing this kind of calculations of a combustor. This is a combustor that has been a test case at DLR in Germany for all the models to compare against it. But these are very expensive. These calculations are very expensive. It is doable, but it is expensive. So the idea is, how we can, improve on this modeling, and how can we transport them on quantum computers, even though quantum computers do not exist yet. How we can do that. So the first part, which I'm going to talk about, is that we said, okay, let's do the modeling of this thing, but not for a big combustor. Let's see that how we can use machine learning techniques. And there's been a lot of talk about machine learning by many people, but we said that how we can use the machine learning techniques and augment it with the physical modeling. And in order to understand some of the some of the terms that inside this PDF or FTF closure that needs to be modeled. So we looked at a simple homogeneous mixing in which we have two reactors coming inside this reactor, and it is considered homogeneous turbulence. And it goes along the reactor, and you get the product coming from the other end. And that is the equation, exact equation for the PDF, in which we have that term, that conditional expected dissipation. That is the term under the second term on the left-hand side need to be modeled. So look, we have this, and we said that if we do the calculations on it, if we, this is the DNS, people do it all the time. If we do the calculations of it, we can get that conditional expected dissipation out of it. So it can come either from the DNS or from experiment, right? Those things can come from this, but those are extremely, people who do this experiment, calculating those conditional expected dissipation is a very expensive thing. We said that, okay, is there a way that we can use this model method in order to model that term? So what we had done, we have been using this physics-informed neural networking. And I bet you guys, these days, anywhere you go, you see this neural networks everywhere, right? I mean, people are kind of see them all the time, but some people are even sick of it. So what we have done with that physics-informed networking is that we said, okay, if we get the PDF coming from somewhere, if PDF coming from experiment or from simulations, how we can use that data to backtrack, like a reverse engineering, all the terms that need to go into it as a closure. And this is essentially, if you're people who do DNS, they do this all the time. They want to capture closure from the simulation. So we said, okay, we want to do this, but we wanted to have satisfy the physics of the problem too. So for this problem, this particular equation has to be satisfied as well. So as we do we make the cost function, minimization of the cost function, we also do the minimization of this term that is involved with a mixing of the turbulent mixing problem. So we said, okay, how does it work? How does it work? Well, but the advantage that we had that if you have been working in this thing for a long time, we always have good cases that you can use for the testing of new models. So back in the 90s, one of the big names in the turbulence modeling was Bob Kraichnan. And Bob Kraichnan was the last postdoc that Albert Einstein had at Princeton. And Bob Kraichnan came up with this amplitude mapping closure. Amplitude mapping closure that was, back then was supposed to be a revolutionary modeling of turbulent mixing. And a couple of my students, Rich Miller, now he's a professor at Clemson, your neighbor, and at the postdoc, Taiwan John, who's now back at Taiwan, we developed this model and extended it for chemically reacting, and we were managing to get some analytical solution of these conditional expectations based on this model. So, okay, this is, and this equation, this analytical expressions, back then it was really difficult to get them. We said, okay, the machine learning method are good. You should reproduce this if the PDF is satisfying the amplitude mapping closure. So we did this. We said, it has a, like a very simple deep learning frame, a number of hidden layer about 10, neuron per layer about 50. And we set it and said, okay, the PDF either coming from anywhere, it could be experiment, or coming from this particular case, we have an analytical solution of it. And, it really, the thing that you get from exact and machine learn with a very small number of neurons is incredible. So the exact PDF is that the machine learning technique sees, And the one that we learned, and for both the dissipate for the PDF and the condition of dissipation, the way, you get that kind of a crossing is very, very impressive. In the sense that, this particular one, it is physically informed. So the machine learning, the deep learning algorithm has not seen any data on it. It has seen the data on another one, but it produces this. So we really think that this is going to be very useful for developing turbulence model of the future. Because in general case, trying to capture that the model is from the DNS data without any other knowledge is going to be very, very difficult. So we are trying this, by the way, all of these calculations are being done by Monte, who worked with us, and now he is a professor of applied math at the University of Colorado. Okay, so that was the example of machine learning. There's a whole bunch more on it that I'm not going to talk about. If you're interested, you can look at the paper. But let's move to the second one, to the machine learning. And, there is a lot of myth about this. A lot of people are talking about it. There's a lot of interest on it. And to a large extent, it has been oversold, in my opinion, in many communities. So what I wanted to tell you is I've had the opportunity to work on it for the past 10 years, and I'm lucky to work with a very good group of theoretical physicists and quantum physicists. So I can tell you stuff that I learned, and I can say to what it can do, what it cannot do. There are some of the things as to what I have seen. So what is quantum computing and quantum information? That's something that started with Richard Feynman back in the 80s. That he claimed that if you're dealing with the quantum system, it says many body problem interaction quantum system. Why do classical computing? But do quantum computing to deal with it. Of course, I have a joint student who's at Oxford, and he's originally from Russia. He says, well, Yuri Menin is the first one who said it. It wasn't Richard Feynman. So that's why I put his name on it. But but this this concept was introduced by Feynman or Yuri Menin. It was a Shor and Grover algorithm in the 1990s that actually made quantum computing something that people have become very interested about. And so that was the birth of quantum computing and quantum information, back in the mid-90s. And if you're really interested on it, I have a huge AIAA journal review article with the whole history of all the basic things in it, very simple. If you're interested, they're all in it. So the first thing, quantum algorithm by Shor, that shows that if you want to factor numbers, factor large numbers, it is much, much faster on a quantum computer. So have many, many applications. And the other one is the Grover algorithm in the search. What you want to do with the searches, that is much faster with quantum computation. And this is what people have known. People have known since 1990. The idea is that, okay, what can you do with it that can be useful for others? And that's what we came in. We coming from engineering side, and we say that, okay, what can we do that can be useful from engineering point of view? But if you look at what is the difference between classical and quantum computing, on the classical side, you always have bits, zeros and one. Zeros and one. Either 1 or 0, right? And in quantum computing, the concept of the qubit, reminds me of myself. When I first came to this country as a foreign student, people asked me, I said, would you like coffee or tea? I say yes. Foreign, coffee or tea, yes. So it is 1 or 0, yes, both at the same time. Both 1 and 0. That was the qubit. The qubit is, and that's And those 1 and 0s are the way that physicists, theoretical physicists, if you take your quantum courses, they represent a vector like that. The vector in Hilbert space, that's a vector 1 and vector 0. So quantum computing has there are two reasons that this thing is very powerful. One is the concept of superposition. Something could be any state phi could be anything, temperature, velocity, concentration. It could be at two states at the same time, 0 and 1 at the same time, okay? So that's one. And how can it be 0 and 1 at the same time like this? This is 0 and 1 at the same time. But once you measure it, then that becomes your reality, right? And in fact, this would be the probability being a state 0, probability being a state 1, summation is 1. But after you measure it, then the probability of any of them would become 1, the one that you observe. The basic of quantum. And the second one is the process of entanglement, okay? Entanglement is that, a state, if you have more than one qubit, it can be represented, the way that the state can be described by 2 to the power of n complex numbers. Okay, so for example, these are now each one of the, all of this qubits coming every 2 to the n qubit, and you would have any state could be represented with all of this. So you have simple, like 1,000 qubits. Your state can be represented by this, and that's about 10 to the power of 300 coefficient. And the physicists, they tell me that this is more than the number of atoms in the universe. I said, are you sure? I mean, that seems small. And they said, well, if you don't believe us, go count them. And this is the number of the things that you can use. And imagine if that is your, if that is the storage of your computations, And so there is a whole bunch of books on it that related to the supernatural and stuff like that, I try not to think like that because my connection with the guy after is not so good, so I just look at them from engineering standpoint. So what is the difference between classical and a quantum computer? The one on the left is just a typical gate, classical gates, zeros and ones, and you have all of the knots and ands and zor and rank and all the other gates. The one on the right are a whole bunch of a lot of these matrix operations. These are all gates. These are all quantum gates, and that's what the operation is done. So this is what exactly quantum computer coming in, quantum state coming in, a whole bunch of gate operations and going on. That's what the result is would look like. And what you have seen in classical computer, you see electronics, zeros and one. In quantum computing, the way they refer to them as spintronics, and you see a lot of this, electron with a spin up and down that represent the vectors zeros and one. So how does the calculation go? So in a classical computing, you start from something, from initial conditions, and you do the calculations. At the end of the calculation, that's what the result are, exactly what it is. Even if you are doing a stochastic calculation, at the end, the result are deterministic. Even if you are doing Monte Carlo or stochastic, at the end, you have everything in hand, you print it, plot it, whatever you do, take a selfies with it, so this is what you have. The thing is right in your hand. Now, what is happening with the quantum computing? You have a start from initial case, then you have initial state, then you have, and immediately, let's say the gate operation, it operated given by Schrödinger equation. So immediately you get a stochastic PDF. I mean, that's what you have, all of the states are in it immediately. And so once you measure it at any point, that's what exactly your measurement is at that point. That's what you're measuring. So the algorithm, the quantum algorithm is that give that measurement with the most accurate accuracy possible. So that's what all of the beauty of the quantum algorithms are. And they have to be written using this entanglement to make the calculation to be more efficient than classical one. That's the whole idea of the quantum computation is. I don't need to talk about this one. There's some of the, so quantum algorithms, that's what we're interested in. You know, so these are, again, you know, there is not really, I mean, there are people talking about that IBM and Google that they have quantum, you know, gate-based universal quantum computers, but they're not really operational, but the algorithms are on it. And the speedup is, you have this Amplitude, enormous Hilbert space because of this superpositions and entanglement. And there are algorithms that are written, and there are, say, some of these people are writing this algorithm or even in mechanical engineering departments. These algorithms are showing that to be a lot more accurate. For example, search algorithms, solving linear algebraic equations, Monte Carlo sampling. So these are for the digital universal quantum computing. People have shown if these machines are there, they're going to be faster. This algorithm, they're faster than the counterpart in classical. You know? So the way we made the use of that for solving this problem, and we solved the same mixing problem, but we modeled the mixing term, because this one is, we have to model it. We modeled it with the Oualescence dispersion model and use the Monte Carlo to solve this. And we solved it Monte Carlo classically and the Monte Carlo by the quantum algorithm. Rolando Sama is a research scientist at Los Alamos. He's a quantum algorithm, and we work with him in devising this algorithm. And the way that these calculations are being done, you know, so if you have a classical problem, classical algorithm, and classical computer, but we have classical problem, we have the quantum algorithm, but we don't have a quantum computer. So we had to mimic this on a classical computer, but using the quantum algorithm, which is very inefficient. It's not an efficient way of doing it, because you know these are built for dumb. But we wanted to demonstrate if the machine was there, if this one was. So this is what we basically get. You know, this is the fuel conversion rate in a plug flow reactor. The one on the top, classical computers. The error of the classical computing that goes as 1 over the square root of the number of realizations in a Monte Carlo routine. You have a Monte Carlo calculation and a what. And the one on the bottom is the quantum that is scaled as 1 over n over 1. So, and these calculations are being done with a large number of particles. So, this is, you know, what we find that is a major breakthrough in this business that shows the error scaling if you are doing classically or by quantum, the quantum being the red one, you get a much, much faster rate. You know, much, much faster rate for this kind of calculations. So if you're a combustion scientist and you want to do this, this is one of the examples in which, you know, one of the examples in which that class quantum computation could be much more productive, much more faster and economical. But one example, we showed there are other examples that people are showing. You know, there are some people are using some of the algorithms solving turbulent pipe flow problems and others. Now there is a problem with digital quantum computations. One of the major problems is the qubits that are in there. They also interact with whatever goes outside. That's what the nature of quantum things are. They cannot isolate this thing. And there is a lot of noise within the system. And this is one of the major problems that people are trying to deal with. One of the major problems with this quantum gate-based universal computer is that any kind of fluctuation, temperature, electromagnetic, whatever, this fluctuation would introduce error and how to make error corrections. So, what are the options? What are the alternatives? I talked about some of them. You know, one of them, something the NISQ computer, people say, okay, it might be some noise in it, but you know, maybe the noise can be tolerated. That's one. There is another one, there is a hybrid quantum classical computers. These are machines that we can do some part of it classically and some part of it in a quantum fashions. And especially a lot of people in chemistry, they kind of like that. They can do some of the calculations, on the quantum and then bring them back. And one of the approaches. And there is an analog quantum computers, or you probably have heard of the DWAVE machine, the quantum simulators. That what they do, they just simulate. It's just a quantum system to begin with, just simulate that particular case in which you know the Hamiltonian of it and you simulate. So these are the approaches that are there. If you're interested to know about them, as I said in my review, I explain them and give references to them, what they are, if you want to know more about it. But the one that we like, and I really think is going to make a big impact, is quantum-inspired algorithms. These are the algorithms that they come from the field of quantum, but we apply them in the classical sense, but the original idea comes from quantum. So if we look at the Schrödinger equation, that equation, one of the things it has, and one of the things quantum physics have to do with, the many-body problem. There's many bodies interacting with each other. And a lot of these interactions, if there are a lot of local interaction might be important, if the faraway interaction may not be that important. But that's the way it is, the turbulences. We have a lot of interactions that are closer, the edges are closer to each other, they interact. The edges at the far, they would dissipate in things, and maybe they have that much correlation with them. So we can see there is a big way that we can connect these two. So, and this is the idea that in quantum physics known as the tensor networking. Tensor networking, it says it's going to become a big thing. Our paper on this one just appeared in Nature last month, Nature Computational Science. And I've been telling people, no, this is going to be the new thing. This tensor networking metric product state is that takes advantage of the entanglement and the way that people want to deal with them in a quantum system. That one could come up and deal with turbulent system. And the key person in this work is my colleagues at Oxford in England, and also the Cambridge Quantum Computing in Cambridge, England. And so what we want to do, what with this tensor networking is something like somewhat, okay, like in CFT, when we have a large number of grid points, what we are saying, what a lot of people have been doing, including myself, when we do LES and everything, we do a scale resolving. We say that we want to not worry about so much about the scale to see how much of the Hilbert space do you need to do your calculations. So if this is the state variable, could it be? And it could be many. So it is, these are all of those, representing as a tensor, as an nth-order tensor, representing this thing as an nth-order tensor. I can always make it as a tensor product of the two smaller Hilbert spaces, right? If I have a big Hilbert space, make it composed of two different Hilbert spaces, and each one of them could become a smaller and smaller. Now, this thing right here, it is in quantum thing, is a Schmidt decomposition, has a lot of similarities to SVDs that you guys do, SVD, singular value decomposition in machine learning. So I can truncate this thing instead of writing them, just truncate them, and then these are the energy that is associated with each one of those scales. So if this is my original field, I can systematically do SVD contract, and finally make them to this original big tensor to be the tensor product of a whole bunch of a smaller one, and do the operation on this one. Okay. So showing how this thing works. The one on the top is a DNS. DNS of a Taylor-Green vortex, the one that fluid dynamic people do all the time. The one at the bottom is an under-resolved DNS. Under-resolved, you're looking at it, it's just capturing, but not as good as the original DNS. Of course, you can show the statistics of it too. But this is the one in the middle that is quantum-inspired metric product state, in which we're comparing. And if you look at this has the same resolution as this kind of complexity, but the results are a lot closer to DNS. So this is the idea that coming from quantum, but it is in a classical way, it is making things to be captured very nice. Now, and this picture is really nice. This is the Schmidt decomposition that shows the interaction between all of the scales. So, these are all the energy. This is the, just one component of the velocity. And this is what the DNS requires. The DNS requires, but this one shows the 99% of the energy at this bounds that are needed. So you don't need this whole bunch of this other ones. So you have this huge space for DNS, big space, big, is a small part of it for your calculation. So I think this approach is just new, the first application of fluid dynamics, and it's going to make an impact as we move along. So that's what the quantum inspired are. And this is again for a temporally developing jet flow. This is the DNS. This is the quantum inspired metric product state and under-resolved DNS. And and as you can see, if you look at the vortex rollup, this you're getting the rollup of the vortices pretty much in time, but this one is totally, lost is, the instabilities and transition to turbulence with the growth of instability loss. Okay, and these are the Reynolds stresses, similar, this too, you will see pretty much the same picture, whereas statistically, your DNS is. And this is something my quantum people are telling us, which I don't know. They're saying that if you're doing tensor networking, they are much easier to actually program a universal computer. This is something I just believe what they say. They have a paper in here, but to be honest, I cannot understand. It's tough, very tough papers for me to read. So what is the status of QC? There are, as you know, Google, IBM, Microsoft are all building this computer. 10 or 50 qubits are not very much operational. People use them, and they say with 50 qubits, you can get quantum supremacy. Some companies are saying that they've already achieved them, other companies say that they're not. So this is what it is. If you have really 50 qubits that you can do calculation without any error, you can get past any classical computers ever. So this is where we are with a physical error rate. And this is the number of qubits that what people are hoping within 5 years we get to 1,000. And as we go further, this is where people would like to have, the fault-tolerant quantum computers. So my last slide is that, the two parts of it, the big data. As we have talked a lot about big data, we need big models. I mean, that's what, the modeling, as the data has to go hand in hand. I think people have gone through the phase of using big data for everything. This might be the time to enhance it with big data, especially now that the amount of data is doubling every 12 months. And pretty soon people are going to say it's going to double every 12 days or 12 hours or whatever. So this amount of huge data is out there, you need big models to take care of it. And in the case of quantum computing, it is real now. I mean, there has been a lot of talk about it, but the way it is going, it is real. And Bill Phillips, the Nobel laureate, saying that what you're comparing, the classical computer to Abacus would be what you would be comparing quantum computers of the future to this. So that's what it's. So this is my last one, maybe the demo, all of my co-authors. But all of these workshops, we organized a couple of these workshops past couple of years. one in machine learning, one in quantum computing. The proceedings of that are available if you are interested in. And thank you very much for your attention.
Thanks so much. Very, very interesting stuff. I'd like to open up the floor for questions for Professor Givi.
And thank you very much for coming on it. I know it is not your seminar day. I'm sitting here for the whole thing. Thank you. If you have any questions here, I could answer. And if you want to answer me later, yes, sir.
Yeah, how would your simulations and the scale with physical scale? So can you use quantum on a flow over an airplane, for example?
Can we use quantum computers for what?
To analyze a turbulent flow or a flow over a commercial airline? Is the technology transferable to those large scale applications, large physical space applications?
Right. So, as I said, the digital based universal computing, the way that we are used to classical computers, they really don't exist. There are algorithms that are written, that, for example, they have shown quantum speedup for Monte Carlo, inversion of matrices, some matrices, they show that quantum algorithm can operate faster. Now, there are some of these machines that encouraging people to go and use them. Like IBM has a summer classes, people can go, the Qiskit machines, and Google has some internship, you can go there and play around with a specific algorithm. So if you say that, okay, I have the CFD code, and I have, I don't know, the star CD or any of this code, I want to run a quantum computer. No, it is not possible at this point. Or general things we do, finite element, finite difference. No, it is not quite at the point is not possible. There are, for example, we will do like a pipe flow problem, they reduce it to solving some aspect of solving, one simple ODE in which you want to invert the metrics. For that, there might be some of the quantum machines that it can use. So it is not ready for practical application the way we are used to. But what we like to do, at least a lot of engineers like to do, to say, okay, let us develop this algorithm and try them out. Problems in combustion turbine or solid mechanics, that when these machines are ready, we can run on them. The other machines, the D-wave machines that are simulators, people don't think they're quantum computers. But those machines, a lot of people are using them. A lot of problem in machine learning, optimizations, quantum chemistry, a lot of people are using them. Los Alamos and NASA, they have bought these machines and are using them for machine learning and other applications, but not for the kind of things that we typically do.
Nice talk, I have a question about memory. So I see the potential if you have an actual quantum computer, if it gets to that level, that I can see the speed up, the CPU speed up. But memory-wise, I haven't heard that much discussion. So if you want to run a 3D equivalent CD problem, and you're carrying hundreds of species, is there a discussion about memory? I see the speed up. I see that you have faster processing and potentially faster algorithms, but the memory can be bottlenecked.
So I don't know. To answer the question, I don't know what to deal with it. But the fact that you can represent a state of a variable by superposition of all of this, so it means that you can be doing this, like a Monte Carlo calculation, for example. You have one realization going, another realization, and realization. With this one, with that the state being represented, you can do them all at the same time. So that's where the speed up coming. But good question is, what do you do with the memory, or storage, and anything else? I don't know. I would not be the right person to answer.
I had one question on that last thing you were doing with tensor. Got the term, but it looked like to me you basically have a better subgrid scale model in some sense coming out of this. Is that correct in the sense that when you go back like a couple of slides, maybe I can't remember the term you used, but if you showed the comparison for that flow in a box, go back.
I'm going the wrong,
I've never done it.
sorry about that.
Anyway, the tensor, the thing you use, what do you call tensor, tensor network,
Uh-huh,
you had a coarse grid DNS, it wasn't too good. You had your model, or your approach that looked very much like the DNS itself,
right,
but at a coarser resolution.
right.
So in some sense, you basically built a subgrid model that accounted for all that stuff in a better way. Is
We did
that
that.
a way to interpret it? Or
We did that. We really did that. What we did, we said, okay, this is the initial field.
Yeah.
This initial field will represent them. So say that you have 120 grid points. We consider that a tensor of 120 rank.
Right.
And we decompose that into a whole bunch of this tensor that are order 2. They're all,
But you had to have the initial field present. What I'm wondering is that could you use that to, instead of having to have the DNS to more or less drive the whole process, could you figure out how to make it work better on the course grid based on knowing what you did?
but this one essentially, but it is not the grid.
Or the,
So it is coarser structure.
okay,
So this is the whole thing.
yeah, I got it.
You know, we say we don't do it on a coarser grid, but we are doing on the coarser structure.
Right.
You know, so it is the whole, essentially this whole idea people are talking about, as you know, we have been doing the modeling at the scale subgrid, you know, we should forget about the subgrid, you know, let's have the structures. If you resolve the structures, and the structures are given by the interactions of all of this tensor with respect to each other. So if you can model that, then you are capturing the physics correctly.
This is just a new way to sort of show insight into what that should be.
Exactly.
Yeah.
That's a, yes.
Super example. I actually had the same question on Jack's question, and exactly on the same slide that he says. So when I look at that matrix product state where they kind of propagate space, that immediately reminded me of this recently very popular Kuhlmann operator theory, right? And is there any kind of comment on that? And because you kind of comment on you are kind of tracking the structure as a solution. And is that something related to you're just kind of changing the basis on that Hilbert space and just kind of find a solution there so they can kind of distribute your solution space to a much more. Is that how it works?
Well, there are, the tensor networking. I mean, we are using one aspect of it. We are using metric product state. And there are other physicists that they say there are other ways of doing tensor networking. So I said there is a whole bunch of different ways, but this is the one we know how to do. And there is a whole bunch of them that I know my friends and theoretical physicists, they know some of them. And they say, there are some, and there are some people who say that some of this other tensor networking would be more efficient way of doing it. But I don't know. I mean, this is the one, and and even this one, I tell you, I struggle to learn it really, because as you know, SVD is very expensive. You cannot just do SVD and do it. So we have to use other techniques of doing equivalent to SVD that is much more efficient of doing the calculation. So there are a whole bunch of other tensor networking people say, I use them in quantum physics, and I'm hoping in the future I can compare them. Good question. So it's really good question. Amazingly good question.
Okay, if that's not the case, I really appreciate and thank our speaker.